Alright, so let's talk about another rule of differentiation called the chain rule. So there are things we can do with functions. We can add functions, we can multiply functions by a constant, we can take the product of two functions, we can take the quotient of two functions. But another thing that we can do is we can take the composition of functions. So suppose we have functions f of x and g of x. Well, we can, so long as we don't have a domain issue, which you have to check for when you're working with this, but at least for every x for which this makes sense, we can define h of x to be equal to f of g of x. We can take x to g of x and take that to f of that, and we can form our composition. Okay, so this is something we can do with functions, something which I imagine you've seen before. So a natural question therefore is, okay, how do we differentiate a composition? And the answer here is actually a little nicer, because here we can talk about lines again. So let's sort of draw, maybe we won't draw a picture quite, but let's just talk about how things work. So let's talk about the derivative of h at x at a. Well, what do we know? We know that near a, we have that g of x looks a lot like the tangent line to g of x. And this is a quick little exercise to see that the tangent line to g of x is itself a function that has this formula. So if you want like a quick and dirty way to write down the tangent line to g of x at a, this is it. And then we have that near g at a, well, how does f at x behave? Well, suppose in the first place that f is differentiable at g at a. Well, we could think about the tangent line, or the linear approximation of f near g at a, and that's going to be, well, f at g of a plus f prime g of a times x minus g at a. Right? So we have these two tangent lines near a. We have that g at x looks like this, and near g at a, we have that f at x looks like this. So now, if we take f of g of x, well, what's that going to be? That's approximately going to be, if we replace f with this approximation here, and if we replace g at x with this approximation here. So let's plug everything in. It's going to look a little messy for a second, but everything's going to cancel. So I'm using, first of all, this approximation for f and this approximation for g, and I'm going to get this. So here's just the approximation for f, but now let's plug in for x this approximation for g, and we're going to get this guy here. But of course these g of a's are going to cancel, so this thing is equal to f of g at a plus f prime g at a, g prime at a times x minus a. And now, I will have to have you draw this sort of in your minds, but the idea is, if we replace this composition of f and g with this composition of the linear approximation of g and the linear approximation of f, this should be good enough to give us a nice linear approximation, that is the tangent line, to this function h at a. And what is the slope of this tangent line? The slope of this tangent line is this number here. All right, so this is the chain rule. This isn't a full, rigorous mathematical proof of the chain rule, though I'll admit, if you sort of cross your T's and dot your I's, you can basically upgrade this idea into one. But what the chain rule says and use this as your guide to see why this is true, is that in this case, h prime at x is indeed going to be equal to f prime of g at x times g prime at x. So that's the chain rule. Let's do some examples with it. So now that we've learnt the statement of the chain rule, let's do some examples. So first, let's talk about a function. Let's call it h of x is equal to x squared plus 3x plus 5 to the power of 100. Now, yes, this is just a polynomial, but why do we like this? Why do we want to be able to use the chain rule here? Because our formula for differentiating polynomials requires the polynomial to be written out all in individual terms. And I don't think anyone, and I certainly don't, wants to raise this polynomial to the power of 100. So what we're going to do is we're going to use the chain rule on this function here. And how do we do this? We want to write this as f of g at x for some f and some g. And this is the difficulty here, figuring out what f and g are. So, and sometimes notationally, and you might have learned it this way or seen it somewhere, sometimes we call this f at u, and we let u is equal to g of x, and sometimes we sort of try to find what u is. You don't have to think about it that way, but this is notation that's everywhere, so I want to put it in front of you. But nonetheless, let's figure out, in this case, what's our f, and what's either our g of x or our u, depending on how you want to put it. But it's not too hard in this case. We have this power of the 100 being on the outside, so we're probably going to want fx to be equal to x to the 100. That's the thing that's being done last. And if we pick f at x is equal to x to the 100, we're going to need, I'll just call it g of x for now, but please note that a lot of sources use this u notation. That forces g of x to be equal to x squared plus 3x plus 5. But now we can differentiate this thing pretty easily. We have that h prime at x by the chain rule is going to be equal to, well, we know the derivative of x to the 100. It's 100x to the 99. So the chain rule says that this thing is going to be 100. We're going to have to toss g in here to the 99. So let's do that. Let's toss g in here. And then we have to multiply this whole guy by the derivative of g. But this is just a degree 2 polynomial, very easy to differentiate. This gives us 2x plus 3. Okay? There aren't further steps. We're done. I think that this is very good news because we differentiated this function actually very, very quickly. And yes, with this power of 99, the numbers would get pretty big, but it's going to be a lot easier to compute values of h prime at x using this formula than it would be to expand this out, get 200 terms, 201 terms, I guess, and then differentiating that down and having to evaluate each of those terms. So this definitely saves us quite a bit of time, and this is why we like the chain rule. Let's do another example here. Let's say we have, all right, this is going to be a little messier. This is deliberate because I just want to show you that things can be messy and it can work out. So let's say we have h of x is going to be equal to, okay, x squared plus 1 to the 14 plus 3 x squared plus 1 to the 4, and all of this is to the 17. So this is a bit of a nightmare, but being a nightmare doesn't mean we can't tackle it. So what do we want to do? Well, in fact, there are two different ways we can go. I'll pick one to start, and then I'll show you how we could do it the other way. And the idea is you actually do have some choice here. The chain rule simply works, so if you find something that works, go for it, but then you might have to do more things. For example, in this case, we're going to have to use the chain rule twice. So let's use the same idea as last time. Everything's being raised to the power of 17, so let's let this outside function be equal to x to the 17, And let's let our g of x, or our u, if you will, be everything on the inside. So I'll just write it down here for space considerations. X squared plus 1 to the 14 plus 3 x squared plus 1 to the 4th. So, by the chain rule, h prime at x is going to be equal to, well, the derivative of x to the 17th is 17, the stuff on the inside, to the 17 minus 1, which is 16. Okay, well, the stuff on the inside is going to be, I'll just write it little here, x squared plus 1 to the 14 plus 3x squared plus 1 to the 4th. But now we have to find what g prime of x is. And I won't rewrite this, just note that this first part of the derivative is essentially done. Now we have to compute g prime at x. But g prime at x, computing that, is something we can use with the chain rule again. Because this function, could we raise this thing to the power of 14, multiply 3 times this thing to the power of 4 together, and differentiate that? Yes, we could. But do we want to? No, I don't think so. So how does this guy work? So let's say we want to write g of x is equal to, let's maybe call it f2 of g2 of x. We want to do this whole chain rule thing a second time. And it's a little tricky to see what the outside guy should be here. It's a little easier up here. But we definitely see this nice little inside guy, x squared plus 1, couched inside of this formula. So let's let g2 of x be equal to x squared plus 1. And actually, because this notation can be useful, let's call this u in this case. So what does this mean? Well, now we can rewrite g of x with this thing being equal to u. And then what do we get? We get that this is u to the 14 plus 3 u to the 4. But this is why you use this notation in the first place. This helps you see that f2 of x, therefore, is going to have to be x to the 14 plus 3x to the 4. So now we can use the chain rule again to differentiate g of x. G prime of x is going to be equal to, well, f2 prime g2 of x times g2 prime of x. So, okay, what's f2 prime? It's complicated enough that we might as well compute it here to the side. f2 prime of x is going to be 14x to the 13 plus 12x cubed. So this thing is going to be, okay, 14x squared plus 1 to the 13 plus 12x squared plus 1 cubed, all times the derivative of x squared plus 1, which is 2x. And now what's the full derivative of h? It's this guy here times this guy here. And yes, this is a long formula, but take a step back and remember, as long as this formula is, it would be much worse to fully expand this guy and need 14 times 17 times 2 plus 1 terms. It's much easier to do it this way. So yes, hopefully you won't get functions this complicated generally. The point of the chain rule isn't always to deal with things that are absolutely this monstrous, but the fact of the matter is that the chain rule can deal with things this monstrous, and nothing else easily can. So this is a reason why we really like the chain rule. Finally, could we have done this in a different order? Yes. We could have, right away, eyeballed this x squared plus 1 on the inside, picked our original g of x as this x squared plus 1 on the inside, rewritten that as u, and everything that remained as a function of u would have been our first function f. We could have then used the chain rule on that, and differentiating g would be easy there, but if we had have done it in that way, the f that we got, we'd then need to differentiate that with the chain rule. But that's fine, we can do it. So it wasn't the right choice in any way, shape, or form to pick f at x is equal to x to the 17th to start. It was just a correct choice, and you can do these problems in various orders. The point is that we can actually solve these problems, which is what we need to do.